Hi everyone, I'm Joaquin van Schoren and welcome to lecture 4 in our machine learning course. And today we'll talk all about model selection, or how to evaluate your models to find the best ones and knowing whether we can trust them. Now, there are many different reasons why we want to evaluate our models. First of all, we want to know whether we can trust our methods if we apply it in practice. Right? That means we need to evaluate it under circumstances which mimic as close as possible how the model is going to be used in real life. Second, we want a way to select between different possible options, between different algorithms, between different hyperparameters. So we need a way, a data-driven way, to measure performance so we can choose which one of the many options will perform the best. Third, we want to convince others that our work is meaningful. We want to convince our peers, our bosses, our clients that the models that we build are useful, and also to convince ourselves that we are doing a good job, of course. And finally, we want to also interpret what the model has learned. Evaluation helps with that. There's also many other techniques that we can use to help interpret our models. Because whenever, even if you find a model that seems to perform well, you need to be very careful. You need to reason about possible explanations why your model may perform well. Right? If it performs well, if a certain metric is good, it doesn't mean that your model has learned the right thing, right? So we need to think about how to test models in different ways. One typical example of this is this paper by Marco Ribeiro, where he showed a case of classifying huskies and wolves from images. And this model worked quite well. It was a deep learning model. But when they looked at which pixels the model was looking at to make classifications, they found that it was basically looking whether there was any snow in the background. Well, so the model did a good job classifying these huskies and wolves, but it did well because in the training data, the wolves typically had snow in the background and huskies didn't. So there can be some bias in your data which can completely distract your model, and you need to be very careful of that. Okay, so evaluation is also a very important part of designing machine learning systems, right? Just choosing your favorite algorithm and sticking with it doesn't always work well. Say, of course, deep learning models work well in many situations, but in other ones they don't. So you always need to be very careful and very adamant in evaluating your model. You also, it's a good idea to consider the problem at large, right? Don't just blindly optimize a metric. Think about how you should really measure success. Typically, the accuracy of a model is not the most interesting thing. We want to see whether it will actually do something good. Right? And depending on the application, this could be making money, it could be saving lives, it could be making scientific discoveries. And when our model makes mistakes, there can be important costs involved, and we may want to include those possible costs in our evaluation. Another question is whether we want to understand phenomena or whether we want to do black box modeling. Right? Do we just want a black box that makes predictions, or do we actually want to explain the predictions or understand a certain phenomena that we're studying? Could be, for instance, some scientific problem. Also, always analyze your model's mistakes and do this early on. Again, it does not help to just blindly optimize a metric. Really think about what the model is doing. Look at the mistakes it makes. And this often gives you a lot of insight on how you can improve the model separate from just tuning it. For instance, if you see that a model is not able to learn some concepts, it could be because your data is biased. Right? So it could mean that you need to collect more data or just get different data. Or maybe you should reformulate the task altogether. Think about these things. And this, as soon as you can identify these issues, the sooner you can find solutions for them and build better models. And all of that is always a very good thing to do because it also makes your model simpler. Right? You can either start from imperfect data and build many complex models on it, or you can really think about how you can make the learning problem better or easier so you can use a simpler model. And simpler models are typically always good in engineering applications. This is, for instance, an image from Google, a paper from people at Google, where they showed that machine learning code is actually only a very small part in real-world systems. So don't focus too much on the model itself. Also think about what's around it. And finally, when we have selected our final model, we're still not done. We now need to test it in the real world. We need to deploy it and see if the outcomes are improved by it. Right? And this can be very tricky, especially because of feedback loops. Sometimes when you deploy a model, it actually changes the data that it will see in the future, which means it will no longer work in the future. Some examples of this are, for instance, medical recommendations. If you find a very good model that can detect a disease, maybe you then make that disease disappear. It no longer shows up in your data. And if the data changes, then your model may not work well anymore. So you need to rebuild your model again. If you build a good spam filter, spammers will find ways to circumvent your filter. So it again needs to learn and needs to update continuously. And trading algorithms can have a profound effect on the behavior of the stock market, and that again may cause all kinds of problems. So you need to also test how it will work in practice. The two very typical ways of evaluating this in the wild are A/B testing and bandit testing. So in A/B testing, we typically have a group of different models, like A, B, and C, and we now want to see which one works best in the real world. One way to do that is to make different measurements. For instance, if you have a group of users or patients, we can maybe divide these in different groups. We use different models on these different groups for a period of time, and after that period, we see which model worked best in practice, and then we use that model for all future users or future patients. Bandit selection is a bit more intelligent in that it doesn't wait for a long time and then makes a decision. It continuously evaluates all different models. And if a model works better than the others, we assign more users to that model, or we make more users benefit from that better model. And if it continues to work well, then we increasingly give it more share until it is then used by everybody. Okay, now there are different ways to evaluate machine learning models. And the crucial aspect of any of these is that you should mimic the real world situations as closely as possible. Right? If you're giving a data set or you have collected a data set, that's only like a snapshot of the real world. And we need to use that in a way that we can test our machine learning models as closely as possible to how to be used in the real world. Now, the simplest case to do that is to just hide part of your data. This is called the holdout. We separate, for instance, 25% of our data, we separate it out, we train our model on the remaining 75%, and then we test it on the unseen hidden future 25%. This is one visualization of this. So here I have a data set with three classes, blue, green, and red. And we are going to create test sets, which means for every class, some points will be training sets, the circles, or will be in the test set, the triangles. Now you may wonder, what's the best way to make this 75-25 split? You can do this in different ways. And if you split it randomly one way, is that the best way to split it? Right? Well, to avoid that problem, what we can do is make multiple splits. And there's different ways of doing that. Now, the most common way of doing this is called cross-validation. It means that we will split the data into a number of folds of equal size. So say that this is our data set. We separate it into 5 different folds, something like that, equal in size. And then we take our first fold and we say this is now our test set, and remaining is now training set. After that, so we train a model on the training set, we test it on the test set, and then we get a score back, score 1. We do the same thing for the second. So then we make the second fold our test set, and the remaining becomes our training set, and this gives us score 2. And so we keep doing that for every fold until we have basically evaluated every point once, and we end up with 5 different scores. Now what we can then do is just take the average over all these scores, and then we report that as the score of the model. And another thing you should do always is to look at the variance. So if you get these 5 numbers, also look at the variance. If you see that this variance is low, you're good. It means that the model is very stable, always gives the same predictions, and gets the same performance no matter which training data it sees. Right? If, however, your variance is large, it means that something is wrong. For instance, it could mean that your model is very sensitive to the exact training data, which means it's overfitting. Right? So that's one sign you should take into account, that maybe your model is overfitting and you need to make it more stable. For instance, you can regularize it or you can get more data. It could also mean that your data has some deficiencies, which makes splitting a bit tricky, and you need to be extra careful about how you split the data. For instance, what could happen is that you have a 3-class data set. Here I have the iris data. I have 3 classes, green, red, and blue. And I happen to separate it like this, which means that now every test set has only examples from one class. This one has only examples from the green class and has string examples from the red and the blue class, but not of the green class. Right? So if you would train a classifier, even if it's the best classifier in the universe, it has only seen red and blue and can never correctly predict the green class. And this happens for all 3 folds, and so effectively we get 3 times 0 performance, 0 accuracy. Right? So we need to be careful in how we split our data. One common problem is that your data can be imbalanced. Right? For instance, here we have only a few examples of the blue class. Now, if you're not careful, it's possible that all of these examples are either all in the training set or all in the test set. Right? Both are very bad because you will never evaluate your model on how well it does in predicting the blue class. Right? Now, to solve that, you can do something called stratification, which means you maintain the proportions between the classes. Right? So if in your original data you have 5% blue examples, you make sure that your test set, all of your test sets, have 5% of test cases of the blue class as well. Right? The way you do that is you order the examples per class, like I did here. You then separate them into case strata, like 1, 2, 3, 4, 5, and you do that for all the different classes. And then finally, your test set of this first fold is the test sets of each class separately joined together. Right? And you do that for all 5 classes, and then you're done. Now, stratification is so obvious, basically, that you should always do this whenever you do classification. There's no good reason not to use it in stratification. It makes less of an impact if your data is nicely balanced and so on, but in practice, it's safe always to use it, so always use it. Now, you could ask yourself the question, how many folds do I need, right? Now, typically, the more folds you have, the better. Why? Because if you have a large number of folds, your training sets are going to be larger. And if your training sets are larger, it's more representative of the full data set, right? So it gives you a better estimate of how well your model will perform on the full data set. You can take this to the extreme, and you can use leave one out cross validation, which basically means that every single point will be its own test set, right? So if you have 100 examples, you build 100 faults and you evaluate your model 100 times. This has a positive thing in that your data is now completely unbiased, right? So no matter how you keep, there's only one way of splitting, right? So it's completely unbiased. Downside, it's very expensive because you need to train 100 models. And if your dataset has 1 million examples, you would have to do 1 million evaluations, so that doesn't make sense. And secondly, it's been shown to actually generalize less well towards unseen data as like a normal k-fold split. And that's because your training sets are very correlated. Like if you look at the test 1 and test 2, the training sets are almost identical, right? So there's a high correlation between all the different faults. And that means it's not really testing the model under very different circumstances in a nice way. And it also means that if you have a different sample, you can get very different results. It really depends on individual points in your test set. Right? Some of these can have 0 performance, some of them get 100% performance. So yeah, there's no averaging at all happening here. And this means it's typically not recommended unless you have very small data sets. Another thing you can do is to shuffle your data. So that means that before you actually start splitting into faults, you first shuffle the data. And this will end up looking like this. So after you shuffle this, so you shuffle all this, and then you split it up, some points will be in the training set and some in the test set, and it will look more or less like this. In this example, basically we said that we have a test set of 25% and remaining 75% are in your training set. However, you can also choose not to do that. You could say that 25% is in your test set and another 25% in your training set, and we just forget about the other 50%. Why? The main reason for this is if your data set is very large and you need to evaluate fast. Right, so say you have 1 million examples, then training all models on 750,000 examples can take a long time. So you can actually get a pretty good estimate by not using all the data, but using enough iterations of part of the data. As long as your training set is large enough not to cause major overfitting, this is pretty useful. Right? Okay. Although never shuffle your data if it's ordered. And that's also why in most machine learning libraries, if you use cross-validation, it's not always shuffled beforehand because it would destroy information if your data is in any way ordered. And a final example of this is the Bootstrap. This is a bit special in that it samples with replacement. Now before we either put a data point in our training set or test set, in Bootstrap, say this is our data set and this is an example, we take the example and put it in the training set, but then we put it back in the data set. We don't remove it, right? We just sample it. So it's possible that after some other samples, we select the sample again. So this means that this point can be in our training set 2, 3, or more times. Now, if you do the statistics of this, it means that on average, every training set, we call it a Bootstrap, every training set has 66% of all the data points in the training set, and the remaining 34% will then be in the test set. We call it the out of Bootstrap sample, or OOB sample. And then we do this k times. This has some nice statistical properties. It's used, for instance, in random forest algorithms, which we will discuss later on. But you can also use it as a separate performance estimation procedure. Now, Another thing you can do is to repeat your cross-validation, and this will definitely help. So you may wonder, if you have your original class and you shuffle that and you take different folds, it still means that after shuffling, you somehow have split the data up in some way. And if you shuffle it again, you will get different test sets. Now, to avoid that sampling bias, you can just do the shuffling n times. So you take your data set, you build a cross-validation, then you shuffle it, you have a new data set, you have a new cross-validation, and you keep doing that for n times. You get something like this. So in this case, we have 3 times 5 cross-validation because you have 3 repeats each time doing 5-fold cross-validation. We call it n times k-fold cross-validation. This is typically, in many cases, the best thing to do. It's relatively unbiased, so the more repeats you do, the better. It's very robust, but also it's more expensive because, of course, you have to build more models. Now, a very important thing to keep in mind is that there are some situations in which you can't just do normal cross-validation. One of these is grouping or blocking. This occurs whenever you have a data set in which you have multiple instances of the same group. For instance, this could be medical data. So every row, every instance is an amount of data about medical testing. But it could be that multiple of these are from the same patient because the same patient came back multiple times. Or it could be like a face recognition system in which you have multiple faces of the same person. Now, if you do that, so say I have this bash data set here, and I split that into training and test sets. Or these just end up to be, some of these points end up to be in the training set, and some points end up in the test set. What it means is that now you're testing your model on people it has already seen before in your training data. Right? This is not good because this means that you want to evaluate your model in how well it recognizes people, new people, in new images, right? And if you evaluate it on people that have seen before, that's not a good representation of the real problem. Right? Now, to avoid that, what we should do is make sure that all these groups are either entirely in the training set or in the test set. Right? And this is called grouping or blocking. It means that you build test sets or more or less equal size by putting together different groups. Like in this one, we only have one group and we're done. This one also one group, here one also one group. No, sorry, here we have one group, here we have also one group, yes. Here we have 2 groups, yellow and purple. This one has pink, green, and blue, and this one has a brown and a light blue. Right. In the extreme, you can also do leave one subject out cross-validation, which is often used in many medical applications. And so you do this k times, each time leaving out one specific group. And then you average overall groups. Now, when data is ordered, none of this will work, right? Because any shuffling or random splitting will destroy the order of the data, right? So if we have some time series data here, if you would randomly choose some points for a test set, it doesn't make sense because you're breaking the relationship between the previous points and the next points. Right? So you need to split the data a little bit more intelligently. And the way this is done is typically called test and train or sequential evaluation, with a more difficult word. What that means is that you look at your time series. So say if I do this like this, so this is time. I will look either for one specific instance or a group of instances called a window, and I train my model with this. Then I take the next example or next group of examples, and I test my model on these points, which will give me my first evaluation point. Then I can train my model again on all my previous data and test it on new incoming data. and again I get the evaluation. So in this case, the evaluations are basically a time series themselves. If this is time and this is the performance, it will actually evolve over time, because sometimes it works better and sometimes it works worst. Hopefully it looks like this, and hopefully it does not look like this, right? It means that your model is just getting worse and worse over time. Okay, you can again average this if you want to, but you can also just look at the curve entirely to see if there's any interesting things that you can learn from that. Visualized in the same way as before, it means that, for instance, we have our train data, the next bunch of data is our test set, and the next case, this can be our train data, this can be the test. Now, we don't have to always use all the previous training data. Right? So say you have after a long while, you've seen a lot of data, and then you have a new test set here. You could evaluate on all this data. You could make this your training set, and this is your test set. But this is not always good, because if your data is actually time series or some evolving data, it means that this old data is no longer really useful. It may be just stale data that does not fit modern or current events anymore, right? And we keep training our model on this old data, which may not be so good. So instead, what we could do is to set a maximum training size or window size. And we basically say, well, we will look back into the past, but no longer than some number W of instances. And so we forget about this data, and we only train on the last window points. Okay, now we've seen a whole range of different evaluation procedures. Let's try to break this down into some guidelines. Now, first of all, when you do classification, always use stratification. Scikit-learn does this by default for most cases, but not always. Be a little bit careful. Whenever you have large data sets, it makes sense to just use a holdout. Why? Because if you have a very large data set, like millions of data points, every subset you make is probably going to be, every random subset you make is probably going to be a good representation of the data. Right? So on a small data set, sampling 25% has a big impact. If you have millions of points, your test sets will be hundreds of thousands of points. So it will still be pretty representable for the real world, or you hope at least. Right? So if you have those situations, using a holdout can be good. It's also often the default strategy for any model that doesn't always converge well, like deep learning. And often we train deep learning models anyway on many examples. Right? So if that's the case, then that's typically okay. There's some debate about this, but if you have large enough data, it does make sense that you don't always need to do cross-validation. Cross-validation still helps you, but it will have less of a benefit than it would have if the data was smaller. Okay, if we choose cross-validation, then we need to choose the number of folds k. If you have a very small data set, like less than 100 or maybe a couple hundred examples, you can use leaf-run cross-validation, because then you test really on every data point once. But if the data set gets larger, it's not recommended anymore, and it's better to use cross-validation. And again, there's different ways to do that. Most popular and accepted methods are either one-time tenfold cross-validation, or something like 5 times twofold cross-validation. There's a lot of papers about that study which are the best ones, but these two are fairly common and used a lot. Well, in some cases, people settle for 5-fold CV, and when you have a very large problem, then that's fine. 3-fold CV is generally discouraged, so at least 5-fold, but 10-fold is typically best. Okay, if you have any grouping in your data, Like if there are groups of instances that belong together and should not be in both your tested and trained set, then always use leave one subject out or grouping. And if you have time series, always choose something like sequential evaluation or train and test or batch versions of that. All right, we've seen how to build train and test sets. The next thing is to decide how you're going to evaluate the predictions. So say I have a training set and I have a test set. I train my model on this and then I give it my test data and my model will give me a number of predictions. Now I want to see whether this actually matches the ground truth y. Are these predictions matching the real world or the ground truth? There's a range of different techniques that we will evaluate. One of them could be, for instance, accuracy, just how close are these predictions to, or are these classes predicted the right classes, or in regression, are the predicted values close to the actual expected values? We could also look at how many mistakes we make over this entire test set and then translate that into a cost. Like how many money does it lose, or how many time is wasted, or how many lives can we not save because our model is not perfect. All these things we can do. Now you may wonder, why do we not just use our loss functions? Right? Because we spend a lot of time trying to find good loss functions that we can efficiently evaluate. Why not just use those? Well, that's because these loss functions, they're good for optimization, but they're almost never what we really want to evaluate in the real world, right? So if your model has a very low squared error, that's fine, but squared error doesn't necessarily mean much to us, right? We may want to think in terms of cost or other things that are more close to our application. And since, well, when we are optimizing our model parameters, we are limited to a certain amount of loss functions. But when we are just comparing the predictions to the actual ground truth, we don't have this restriction. So we can use any metric which makes sense in the real world. And we'll also use that to optimize our hyperparameters. Typically, we don't need loss functions to tune these, although there exist techniques to do that, like bi-level optimization techniques. We'll come back to that later. But generally, we want to tune the hyperparameters to the specific application that we have in mind. The first kind of evaluation that we will be looking at is binary classification. And so here we classify where there are only two classes, a positive and a negative class. Now this means there can only be two types of errors. Either an error is a false positive, which means you predict a positive while actually it's not positive, it's negative. Or it could be a false negative, which means that you predict negative while the example is actually positive. And these two are not always equally important, right? So this is one example where you have a man who comes to a doctor and the doctor says you're pregnant. Of course, this is a type 1 error. It's a false positive. The person cannot be pregnant. Well, in this case, the woman is obviously pregnant, but the test set is that she isn't. So that's a false negative. And the two are really not equal. And depending on the application, one is more important than the other. One example is, for instance, a medical test. If you have developed a test for detecting cancer, for instance, you could have one test which predicts positive a bit too much, too quickly, right? So it means it has a lot of false positive and a few false negatives. This is not ideal because it means that you will predict positive even though the person does not have cancer. This causes distress, causes anxiety. It means spending money on more tests. The opposite actually is worse. So if you have a lot of false negatives and a few false positives, it means you miss a number of cases where the person has cancer. And so this will have some cost, but this will have a much larger cost because, well, now you're not detecting cancer and those people may actually die. Or they may have to go, it will be detected at a later stage, at what time you need to spend a lot more money um, in therapy to recover from that. So it's definitely important to think about your application and what kind of error you're most happy to have. You can summarize all these outcomes in a confusion matrix. The confusion matrix is simply a matrix in which all the actual classes are in the rows and all the predicted classes are in the column. Right? So if you have negative examples, you either predict it negatively, that's a true negative, or you predict positive while it's negative, that's a false positive. If you have a positive example and you predict negative, that's a false negative. If you predict positive, that's true positive. And so you get a matrix of numbers like this. So in this case, we have 48 true negatives, 85 true positives, which is good. But you also have 5 false negatives and 5 false positives, which you want to avoid. Now, the first measure we can take from this is accuracy. And accuracy is, I think, the most well known. It's simply the number of correct predictions over the number of all possible predictions. This is almost never a good metric in real life because, say for instance, you have a credit card fraud detection problem, right? And you have a model that's 99.99% accurate. If there are only few cases of fraud, right? If there are only like 0.001% of transactions which are fraudulent, you may not be detecting them. You may just always be predicted positive and you're simply not detecting any fraud cases, which means your model is basically useless. Right? So just having a high accuracy doesn't mean much, especially if you have high imbalance in your data. To make this a bit more clear, here you have 3 cases, 3 different models, which each give different types of predictions. And they all have the same accuracy. So this model never predicts positive, it always predicts negative. So in this data set, we have a 90-10 imbalance. So by just predicting negative, it's actually already 90% accurate. This model is a bit better, so it predicts 80% of the positives correctly, 10% of these, sorry, it predicts 80%, 80 of the negatives correctly, and it predicts 10 of the negative cases incorrectly. But it does predict the remaining 10 positive examples correctly. Now, here as well, we only have 10% misclassifications. In this case, they are all false positives. But again, our accuracy is the same. And here, this model predicts 85 negatives, true negatives, and all the rest is the other classes. So these are 3 different models, but we cannot distinguish between them. Even though one of these may be better than another, we cannot distinguish them based on accuracy alone. Another metric, which is simply more useful, is precision. So precision you use whenever you want to limit false positives. So if false positives are very bad, think about precision. Precision is defined as the number of true positives over all the predicted positives. Right, so if you look at our matrix here, it means we're looking at the true positives and the false positives. So predicted positive, but actually negative. So it means that precision is basically only looking at this column all the time. So it's completely ignoring the other one. Okay. If you compute this here, so in this case we have no positives, so precision is 0, which is sort of good because we don't want this model, right? It's a bit too simple. This model has a precision of 50% because it has 10 true positives, but also 10 false positives. And also here, it has a precision of 0.5 because it has 5 positives and 5 false negatives. It ignores any false negatives. This is a useful metric, for instance, in clinical trials, like I said before, right? If you have if you have a clinical trial, it means that you are testing a drug, and testing a drug is very expensive. So any false positive means you have to invest a lot of money into them. Right? Search engines are another example. If you have a false positive, it means that you predict that a site or a link is good, but it's actually not. Right? Which means you will have many useless links on the first page of results, which you do not want. Right? So precision is important. Right? We want precise predictions, which means that the predictions that are actually on our first page of search results should be all good. Sort of the opposite of precision is recall. You use this when you want to limit false negatives. For instance, in our cancer test, you want to limit false negatives because it means you're not detecting the disease. Also, in search engines, you don't want false negatives because it means you're not showing the link that the person is searching for. So, in case of search engines, you want to actually have both high recall and high precision. Recall is a very old metric. It's also used sensitivity, hit rate, or true positive rate. It's all exactly the same. It's defined as the number of true positives over the number of true positives plus false negatives. So the number of true positives over sum of the true positives and false negatives. So it only looks at this row here. It ignores the rest. Which means that in our first case, we have true positive 0 over 10. That's again 0. We call it 0. Here, our recall is perfect because we have 10 true positives and no false negatives. So perfect recall. And in this case, it's 50-50. So we have 5 true positives, but also 5 false negatives. So that's 0.5. So recall is of the cases we should detect, how many of them do we actually detect? This is a schematic interpretation of the same thing. So here we have the actual positives here and the actual negatives here. And our model predicts all of these. Right? So these are predicted ones. Now, these are the ones that our model selects as positives. And so some of these points here, are true positives. Right? These are the points of the actual positives that we detect. These are the points, so all the other ones here are the positives that we don't detect. They're false negatives. We predict negative while they're actually positive. In the red here are our false positives. So we predict positive while it's actually negative. And the remaining here are the true negatives. So there are negatives and we predict negative. So in this case, precision is basically the true positives over all the positives. While recall is the true positives over all the actual positives. All right, if you want to optimize both precision and recall, you can combine them in some way. And there are many different ways of doing that. And one of the most common one is the F1 score, which is basically just the harmonic average of the two. So it's precision times recall divided by precision plus recall times 2. This takes into account everything but the true negatives. And it gives basically some score in the middle. So here we had 0 precision and 0 recall. So again, F score is 0. Here we had 50% precision and 100% recall, and today we end up with about 76. And here we had 50% precision and 50% recall, and so our F-score is also again 0.5. Now these are just some of the metrics that we can actually use. There's a nice page on Wikipedia where you can see all the different models, the whole measure zoo. And there's others which are used a lot. And it's interesting to definitely look at those, but we'll stick to the ones we have for now. Okay, what happens if you have multi-class classification? There's different ways you can do it. So there exist actual metrics that work on multi-class by themselves, but we can also use binary measures for multi-class classification. And the way we do that is by retrain the model per class. So if you have 3 classes, we'd say, okay, first model, well, class 1 is our true class, and 2 and 3 is our negative class. Then we say class 2 is our positive, and 1 and 3 is our negative, and then finally 3 is positive, and 1 and 2 are negative. Right? Is positive, is negative. So we end up with 3 different models. We have 3 different confusion matrices basically, and from that we can then average these out. And there are different ways of doing that. So the first and most common, but probably least useful, is microaveraging. This simply counts the total amount of true positives, false negatives, and so on, and then computes the metrics as usual. Right? So precision, as we saw, was true positive over true positive plus false positive. So in a multi-class setting, we just take the sum of all the true positives per class divided by the sum of all the positives per class plus the sum of all the false positives per class. Okay, and you use this measure whenever every sample is equally important. And it doesn't matter to which class these belong. Right? So classes aren't equally important, but samples are equally important, and you should weigh every example in your dataset equally. Now, if you would look at this in more detail, you'll find that micro precision, micro recall, micro F1, and accuracy all are the exact same metric. And just to visualize that, say that we have 2 classes, right? Just for argument's sake, the sum of all true positives per class would be the true positives of class 1 plus the true positives of class 2. And the true positives of class 2 are flipped, right? So that this means it's the true negatives. And you do the same for the other 2, and you will find that you will get accuracy. Right? So all these micro averages are the same as accuracy. So you will often find them being called accuracy as well. Okay, another thing you can do is called microaveraging. Here you average the scores per class, right? So you build the 3 models, you compute the precision for class 1, you compute the precision for class 2, and you compute the precision for class 3, and then you take the average of them. You sum and you divide by 3, right? Which is like this, right? You compute the precisions for every class independently, you sum up and you divide by 3. This is also called balanced accuracy. Right? It's like accuracy, but it's more balanced because you take into account the size of the classes. So you take into account that each class is equally important. Let's say you have 3 classes, and it doesn't matter how many examples there are of each class weighs equally. And this is good whenever you have imbalanced data sets, right? So say you have a data set where you have a lot of examples in the first 2 classes, but a very small amount in the last class, or even in the binary case, you can use that. It means that even if this small class As a few examples, it will weigh equally in the sum of the scores. So this is definitely recommended whenever you have imbalanced data sets. And balanced accuracy is the same as macro average recall. Just remember it. So balanced accuracy is a useful method. It's the same as macro averaged recall. Okay, final thing you can do is weighted averaging, and here you weight the different scores by how many examples there are in each class. Right? So you compute precision for each class separately, and you weight it by how many examples there are in the class. This is less useful if you have imbalance because your small class will weigh less in the total score. But there may also be many applications where this is what you want, right? So you have something that's very unlikely to occur. You may want to weigh less in the evaluation, so you can use something like weighted average for that. Okay, let's see how they look in real life. So here we have, again, our three classes. And let's see how these can be averaged. So first of all, we have our case where we only predict negative. So in this case, so our precision for class 1 here, that's 0 now, right? As before. Now we also compute this for class 0. And in class 0, it's actually correct 90% of the time. So the precision here is 90. Okay. Recall, here we had, for class 1, we had 2 pulses was 0 divided by whatever. This gives us 0 recall. And here we have 90 divided by 90, that's 1. So recall is perfect. Okay. And the F-score is just the average of those. Now, if you look at the micro average, is just called accuracy here. It's all the same, it's 0.9. The micro average of precision is now the average of these two. And this is 45.45. And that's because, of course, precision of class 1 was 0, and this drags down the micro average. Same recall. Because we had this 0 here, again, get a very low score for recall. Right? So this is a very effective method whenever you have kind of imbalanced data sets, or it guards against dummy classifiers which only predict the majority class. And the weighted average is like a weighted version in between. The second case here, you can do all these computations again. This case is a bit more balanced, right? So in this case, we don't have the dummy classifier. It does try to make some predictions. And you see this is rewarded by the macro average is much higher now. But it has still many false negatives. No, sorry, false positives. No, false negatives. And this will weigh on the precision score. And in this case, this is fairly balanced. So the number of false positives and false negatives is the same. So you don't see any difference between precision and recall. They're all the same. Okay, so these are the simplest ones. Now we can look at measures that are probabilistic. Because as you remember, in a linear model class, for instance, when we build a classifier or a regressor, we actually get a function back. And this function makes a prediction, a number, predicting how sure or how convinced the model is that the point should belong to class 1 or class 2, right? So we evaluate our function. If this is smaller than 0, we predict -1. If it's larger than 0, we predict class 2. That's how we defined and fitted this function. Now remember, if you have a decision boundary, points close to it will have a very small decision value, like 0.1. And the same for the negatives, there will be negative 0.1. While points very far away can have a much larger decision value, like 10, or in this case, -10. So we do want to take that into account, right? So if our model is good, it should classify the positive points convincingly. Right? So a model that predicts is very convinced of the positive points and it's correct about that convinceness, then that's a good model. Right? If it makes a mistake, we do want to see that reflected. So if we have like a positive point here and it says that this point is, well, it's minus 0.1. So we think it's negative, but we're not so sure about that. That's better than having the same point with a decision score of minus 10. So in that case, the model would think that this point is very surely negative while it's not, right? So we do want to take it into account when we evaluate our model. There's different ways that we can retrieve this value, this predicted value from the classifier. Most classifiers have a decision function, and we can just evaluate the decision function and get basically a number back for every sample. Some models are also probabilistic. For instance, logistic regression is a probabilistic method. So it actually gives us a probability of positiveness for each point. Well, it will give probability of being positive and probability of being negative for each point. If you visualize that, this is again our decision function. We see here that this is the boundary, but if you would look at, and this is what it typically has, this is negative, this is positive. But if we would look at the decision score, we can see it's actually not so clear cut, right? So around here, it's more or less 0. And here it will be darker, it will be more negative, and down here it will be more positive, darker red. So for each point, we can get how sure it is that it's positive or negative, and we can use that. Now, the decision function is not limited. It basically goes from minus infinity to plus infinity, although in practice it's much more bounded than that, which makes this a bit hard to interpret sometimes. Some models can also give you a probability, which is more or less the same, except it's between 0 and 1. And the threshold is typically at 0.5. And it typically gives you a more crisp prediction, and it's also more interpretable. So we can actually interpret what 80% probability means. Now, where we set this threshold, like here we set the threshold at 0.5, but this is an assumption. There's actually no reason to always choose 0.5, and we can tune this threshold depending on the application. So for instance here, we have two classes, the blue ones, the negatives, and the red ones, the positives. We use a support vector machine with an RBF kernel, which will give us a decision function like this. It's like this oval shape here. If you would cut through this plane here and look at the decision function, it will look something like this. Right? So it's an RBF kernel, it's a Gaussian kernel. So we will typically, if we have data like this, it will typically look a bit like this, the decision function. Right? And so by default, we put the threshold of this at 0. So at this threshold, every point which has a decision value higher than 0 will be positive. So all the points here will be positive. So we see some of these points are actually positive and some of them are false negative. Right? So from this you can compute precision and recall. So apparently in this case, like you can see better here, so here we have all the red points here are only 23% of all red points. Right? So recall is quite low. Precision is a little bit better. Right? So of all the ones in the circle, many of them are actually red. So precision is 0.6. Now, if recall is important to us, we can decide not to stick to the 0 threshold. We can actually lower the threshold, and that will give us a higher recall. but also give us typically a smaller precision. You can see that as I lower this threshold, right, so now all the points in this band are positive. Recall has gone up to 53, and precision has reduced a bit to 85. You can see the circle becoming wider, so it's capturing more of the red points. That's actually, which is good. These are the true positives, but it's also capturing a number of blue points, which are now false positives. And I can keep decreasing the threshold until at some point I'm happy with this precision recall trade-off. So now they are the same. If I need an even higher recall, I can push a little bit harder. So now I end up with 77% recall and 85% precision. So depending on the application, this could be better, right? If you really want recall, this is a better model because it captures more of these red points. Now, if you take it too far, you get some weird behavior. You will see that it gets pretty specific about the areas which are positive and negative. So this is starting to get a bit weird. There's a limit to how far you can push this. Typically, you only look at precision recall and you see what it does. Don't drive this too hard because you may end up with weirder predictions. Okay, if we do this, so if we change this threshold and we record every possible precision and recall, right? So we sweep from minus something to plus something. We will find all the possible precision and recall points. Now, if we plot all of these points on a graph, we get the precision recall curve. Right? So in this case, this was our threshold 0, which had a recall of 65 something, and precision also of 65. And if I change the threshold, so if I decrease the threshold, it means I get more positives. I get more true positives, so recall goes up. I may also get a few more false positives, right? So precision goes down a bit. And if I increase the threshold, it means I will have fewer positives. So it means I have fewer true positives, recall goes down. But I also may end up with fewer false positives, which means precision will go up a bit. So, and you can basically look at this curve and see where the interesting trade-offs are. For instance, if you are primarily interested in recall, you may recognize that this point somewhere here is interesting, right? Because it has high recall, it has slightly lower precision than the original predictions. It's a little bit. But if I would increase recall even more, that would be bad because it would, precision crashes after that point. So here, 0.99, that's more or less our optimal threshold if I want to have high recall and still reasonable precision. Okay, you will often see this jagged performance here, precision values. That's because if you make the threshold very large, you only get a few points left, and this every single point then has a huge effect on the prediction, so it becomes very jagged in this area. Now, this precision recall curve will look different for every model that you try, and even for every hyperparameter. So if I replace the supervacuum machine with random forest, you'll see this a bit smoother. Also, in random forest, it gives you probabilities, so you can only change between 0 and 1. But it's the same behavior. I can increase threshold. I increase the threshold, and for each threshold, I again get a certain precision recall trade-off. All right. So you can use this also to choose between models. So in this case, I have the supervacuum machine in blue and the random forest in red. And you can see that, well, both of them give you different trade-offs. In the central area, which is like average recall and pretty high precision, in that case, supervised machines dominate. They have a higher precision for the same recall than a forced. Right? However, there are some possible models, some thresholds, in which I can get a higher recall from an forced without losing so much precision. So if I want this point here, then my random forest may be better. And vice versa, if I want super high precision, maybe, yeah, in this area, random forest again is slightly better. So it's a good way to look at where different models are better. So if you want to have really high recall, in this case, random forest will be better because I can choose a threshold here, which gives me a better recall for the same precision than supervised machines does. But if I'm happy with 50% recall, then supervised machines are better because they give me higher precision for the same recall. If you don't want to look at the curve, you just want to have a quick estimate, what you can use is the area under the precision recall curve, or the AUPRC. So it's just the area under the red curve and the area under the blue curve. And in this case, these are quite similar. So in this case, the supervised machine is slightly better. It has the area of 0.66, while random forest has 0.658. Right? So the supervised machine is slightly better if you just look at the area, but again, looking at the curves gives you a lot more detail and shows you possible models, possible thresholds that you can use, which may be better for your application. And again, next to the models, also different hyperparameters have an effect on precision recall, of course. For instance, if I use gamma, gamma is a known regularizer, right? So if I make gamma smaller, my kernels get wider, and so it's more regularized. So it may underfit a bit more. If I make gamma too large, you get very narrow kernels, and it's more overfitting. But again, you can see what this means for different trade-offs. Right? So if I don't like my default red one, I can reduce gamma, which gives me the blue curve, and here I can get better recall than I have with the red gamma value. Right? So I can find a solution here which is higher recall for the same precision than I had with the red setting with gamma 0.05. So again, I can do this for different hyperparameters and then see that gives me a better, more useful model for your application. Another interesting thing to look at is the receiver operating characteristic curve. It's a mountful. What this does, it compares the true positive rate, or recall, it's the same thing, right? So the amount of true positives over all positive predictions versus a false positive rate. That's the amount of false positives over all negative predictions, negative values. So every point on this curve, every model will again be 1 point on this curve for every threshold. Now the name comes from early work in telephone lines, right, where the true positive rate is the number of correct positive signals coming out to a telephone line, and false positive rate is the number of signals coming from a telephone line which are actually false positives. It's a measure of how clean your signal is, basically. So we can do the same thing as before. So for every threshold, we will have a certain trade-off. So if this is my let's go ahead. Let's switch back to okay. So our default here was here, so it's threshold 0. Now, if I want more true positives, right? I want to increase my true positive rate. I can do that by lowering the threshold. Right? So if I lower the threshold, both my true positives and false negatives will go up. If the true positives goes up, my true positive rate goes up. If my false positives goes up, my false positive rate goes up. Right? So you can see that lowering the threshold increases both values. If I care mostly about the true positives and I'm okay with the number of false positives, then I can just reduce the threshold to a point like here, where I have 90% recall and just 10% false positives. If I do care a lot about false positives, then again I can increase the threshold so that it will produce fewer positives overall, hopefully also fewer false positives, but it will come at the cost of also having fewer true positives. Right? And again, same thing for different classifiers, they behave differently. This is a visualization of these ratios in a probably easier way. So in this figure here, I have all the points in my data set which are actually the positive class. Right? So all my positive points are in this histogram. And on the x-axis here, I have the decision value. That's what the model predicts for each point. So ideally, if you have a good model, all your points will be here. The positive points, so your model should predict them as positive. In reality, what this model does, it does indeed do a good job. Many points that are positive are predicted as positive, so they are true positives, but also some positive points are predicted as negative because they fall below the threshold here. These are the false negatives. If we look at the negative points, the opposite. So here I would hope that my model classifies them as negative. And it does, again, a good job. So many points are very negative. But also, these are the true negatives, but also some points are predicted positive. So these are the false positives. And the true positive rate, or recall, is simply, of all these positive points, how many are red? And so it's red divided by red plus pink. So it's a ratio of all these points, all the red points, over all possible points. If I want this to increase, I can do that by lowering the threshold. I can lower the threshold, and this would mean that I get more true positives and fewer false negatives. Right? So my true positive rate goes up. This comes at the cost of more false positives. Right? So here I have the false positive rate. So false positive rate is the number of false positives, here in cyan, divided by all the negative points. And here I initially have few false positives, but if I would decrease my threshold too much, more and more of my true negatives will be predicted as false positives. Right? So, and that means my false positive rate goes up. On the other hand, if I want to reduce the amount of false positive, if that's the most important thing, then I can just increase my threshold. So I'll end up with fewer false positives. But this will come at the cost of having fewer true positives as well. If you do this sort, you can drive this, I think, all the way over here until some point here, where you're still okay. You have very low false positive rate for still reasonable true positive rate. But if you take it too far, then this whole big red bump will fall on this side of the threshold, and then the true positive rate will crash. And again, some models can achieve trade-offs that others just can't. Right? In this case, for instance, we can see a small vector machine in green and random forest in yellow, and we can see that if we want primarily a high true positive rate, we can see that the supervised machine affords us solutions which are slightly better for the same false positive rate than the random forest classifier. If, on the other hand, we really want to drive down the false positives, we can see that there are solutions for random forest which are not achievable for the support vector machine, unless we change gamma, perhaps. Now, a very interesting property of the RSC curve is that both random guessing and models that only predict the majority class both have the lowest possible AC, 0.5. If you are random guessing, it means you will randomly predict the positive point as positive or negative. So the true positive rate and the false positive rate are exactly the same. So all these points will end up on this diagonal. And then the area under this diagonal will be 0.5. If your model always predicts the majority class, then the threshold doesn't really make sense. It will always, no matter which threshold you use, it will always predict positive. So in that case, the true positive rate and the false positive rate are both equal to 1. So we have 1 point here, and again, our area under this line basically will be 0.5. Now, in principle, it's possible that you find models which have a curve that's below the diagonal. Right? So it could be something like this. In that case, your AUC is lower than 0.5. But in that case, if you observe that, you can just flip the prediction and then you will find this curve. Only a model that has 0.5 AUC is truly irredeemable. It's the worst you can have. This makes AUC very useful for imbalanced data set. Right? So any model that does not pay attention to the minority class will get a very low AUC score. That's why it's one of the most often used metrics whenever you have imbalanced data. If you have multiple classes, you can still compute the area under the log curve or the area under the precision recall curve. What you basically do is, again, you build 3 different models. Every time you have one class is positive and the others is negatives, and you will then end up with 3 log curves. In this case, this blue one here, this blue one here, and then this brown one here, right? And then you average those. And again, you can choose. You can use a micro average, or you can use a macro average. And again, typically, whenever you have imbalanced data, the macro average is preferred.